Hey everybody, let's talk about synthesis reactions, also known as a composition or a combination reaction. So this is a reaction where we're going to take two different things and we are going to combine them into one compound. So you'll notice that all of these types of reactions finish with just a single compound on the product side. Now, this box that you see in front of you, this is something that you're going to be provided with on a test. It's not something that you need to memorize, but it is extremely useful as we're working through these. So first off, what I'd like to do is have us provide some letters for each of these reaction types. So for instance, we're going to say that a metal plus oxygen, we're going to call that letter A. We're going to say a metal oxide plus water is letter B. Metal plus nonmetal is letter C. I'm going to change colors here because now we're going into covalent. Metal oxide plus nonmetal oxide is going to be D. A nonmetal plus oxygen is going to be E. And a nonmetal oxide plus water is going to be F. So before we go further in the video, let me show you the resources that you have at your disposal, and you may want to take these out. So first off, you're going to want yourself a periodic table so that you can identify charges and figure out what crosses with what. You're also going to want your whole year resources sheet, and in particular, you'll notice that box that I was just writing on is provided right up here in the chemical reaction prediction rules. So remember, you'll get this on a test. You'll notice that things are a little bit out of order on this page that we're looking at currently, but you can make sense of it based on all 6 of these names on the left-hand side. So as we look more closely at that box, what does it mean to have a metal and an oxygen? Well, as a reminder, a metal is anything on the periodic table that is to the left of this staircase. So anything over here is a metal. So if you take a metal and you react with oxygen, you're going to make a metal oxide. If you take a metal oxide, what's that? Well, it's something that's already a metal combined with oxygen, and you react with water, what's that? H2O. You're going to make something else. So what this box is telling us is what we can predict to make based on the starting ingredients, if you will, in our chemical reaction. So what I'd first like to do is go down to the 6 practice problems, and I'd like us to define what we are looking at on the reactant side. So for instance, in number 1, I see K2O plus SO3. So what are those? K2O is made up of a metal plus oxygen, and SO3 is made up of a nonmetal plus oxygen. So really what I'm looking at here is a metal oxide plus a nonmetal oxide. Find that on the table. Metal oxide plus a nonmetal oxide, you'll notice that is letter D. So I'm just going to write a letter D next to this so that we can come back and do that one in the right order. Looking at number 2, Mg plus O, what is that? Well, Mg is a metal, O is oxygen, so this must be letter A, metal plus oxygen. If you'd like to try the video, pause the video and try the rest on your own, feel free, and then we'll catch up. So look at number 3, CO2 and H2O. CO2 is a nonmetal oxide. How do I know that? It's made of a nonmetal, carbon, and oxygen. So nonmetal oxide plus water, you'll notice that is letter F. So we'll put in an F here. We have in number 4, we have carbon plus oxygen. So carbon plus oxygen is a nonmetal plus oxygen. Carbon's a nonmetal. That is letter E for us. Number 5, sodium plus chlorine. Sodium plus chlorine is just a metal plus a nonmetal, so we've put that as letter C at the top. And then finally, in number 6, we have a metallic oxide plus water. How do I know that MgO is metallic oxide? Because Mg is a metal and O makes it the oxide, so that is letter B. So once we've identified all of those letters, you'll notice that I've made some blue and some pink. And there's a distinction between how we do the blue ones and how we do the pink ones. And you'll notice all of the blue ones are ionic compounds. So we are producing at the end of the day an ionic compound, something that has a metal in it. Whereas on the pink ones, we are producing covalent compounds, or things that are made up of nonmetals, with the one exception of this one, which is an ionic compound, but it has a polyatomic ion in it, and the polyatomic ion is made from nonmetals. So we are going to do the blue ones first because they're more straightforward, they deal with crossing charges, and then we'll come back to the pink ones because they're a little bit more complicated. As a side note, you'll notice these special synthesis. These are things that we need to know about. So we need to know that if ever nitrogen and hydrogen are together, they come together to make ammonia. And similarly, if ammonia is in the presence of water, it's going to make ammonium hydroxide. But you'll notice those are provided for you on your whole year resources page. And this is something you'd have on a test. So just keep those in the back of your mind. Anything dealing with ammonia is this special case, but you have that given to you on a test for you to take advantage of. Okay, so let's go in order. We're going to do the blue ones first. I'm going to start with letter A. And you'll notice in letter A, it tells us that if we put together a metal and an oxygen, we are going to make a metal oxide. So what is a metal oxide? It's the metal combined with oxygen. But here's the thing that we know about this. So looking at letter A here, which is number 2, if we combine Mg and O2, a lot of people want to say, oh yeah, that's MgO2. And from math class, that makes a great deal of sense. Unfortunately, in chemistry, it's not like math because we know that magnesium and oxygen both have a charge associated with them, right? So we know that magnesium, it likes to be a +2. And oxygen, when it ionizes, forms a -2 charge. So if you're going to put a +2 with a -2, you don't need 2 oxygens, you need 1 oxygen. So really, this makes MgO. And we would need to balance, so we are going to deal with this discrepancy of 2 on one side and 1 on the other. But remember, we do balancing with coefficients, like so, not with subscripts, because the only way to make a neutral compound out of Mg and O is to put 1 Mg with 1 O. Looking at letter B, so letter B tells us that a metallic oxide and water is going to make a metal hydroxide. So metallic oxide and water, we're making a metal hydroxide. And by the way, hydroxides are bases, as we'll learn later in the year. So we can just assume that we're making a base here, but a base is indeed one of these metal hydroxide things. So as we look at letter B, we're trying to make a metal hydroxide. Well, we know part of the compound that we're going to make, right? We know that hydroxide is OH minus 1. That's great news. But we also need to put a metal with it. So where is the metal? Well, it's not oxygen, that's a nonmetal. It's not hydrogen, that's a nonmetal. It's not oxygen, that's a nonmetal, right? So it has to be magnesium. It must be this one. We know that magnesium has a +2 charge. So we're going to put that over here, and we are going to cross our elements to make Mg parentheses OH, right? You need 2 of the entire ion, parentheses OH2. Now, if you're wondering, well, wait a second, there are a ton of metals, why can't it be iron hydroxide or something? The reason is that you can't magically bring elements in that aren't part of the reaction already, right? So the only metal in this reaction is Mg. That's why Mg has to show up on both sides. We would need to balance this thing up, but it turns out it's already balanced, so either leave it alone or put in a coefficient of 1 in every spot, because there's 1 Mg on both sides, 2 O's on both sides, and 2 H's. Looking at letter C says if we have a metal and a nonmetal, we're simply going to make a binary ionic compound. Well, a binary ionic compound is simply charging or crossing those charges correctly. So again, we can't make this NaCl2, right? Why is that? Because Na is a +1, Cl is a -1. So when we put those together, we need 1 Na and 1 Cl. And if you're wondering, why does this have a 2 here? Remember, that's a diatomic element. It's one that always has to have a 2 if it's by itself for stability. Now, we would need to balance this thing up. We need to get 2 chlorines on both sides, but now we need 2 sodiums, so it would balance like so. Okay, so that's our look at ionic compounds, the blue ones. Those are more straightforward. You'll notice all we're doing is identifying the charges of everything that's involved. We're crossing those charges. We're figuring out what ionic compound we need to make. Things get a little bit more difficult as we attack the pink ones, so letters D, E, and F. And the reason is that now we're dealing with nonmetals, and typically nonmetals and oxygen. And nonmetals and oxygen don't always come together well, right? So for instance, you know that the compound CO exists. You know that the compound CO2 exists, right? So there's no real way just to predict which one of those is going to happen in a compound without doing some tricky things. So what I'm going to show you here is a bit of a shortcut. It's a shortcut that serves our purposes well in honors chem. If we go on to something like AP or a college level chemistry, we may clean this up a bit further. So we are taking a shortcut here, but again, it's a shortcut that works for our purposes for now. So here's our shortcut. If we look at letter D tells us that if you put together metal oxide and non-metallic oxide, you are going to make a ternary ionic compound. So a ternary ionic compound basically means a metal plus a polyatomic ion. Right, so we're putting together a metal and a polyatomic ion. And if you look at the one that we're doing, K2O plus SO3, there's only one metal here. The metal involved is K with a +1 charge. Right? So K plus 1 is the only metal in that entire compound. Sulfur is a nonmetal, oxygen is a nonmetal. And so it turns out that if we're putting that metal with a polyatomic ion, there are some polyatomic ions that we know that involve whatever's left, which happens to be oxygen and sulfur, right? So we know that the polyatomic ion SO4 with a -2 charge, remember that is sulfate, with an AT ending. That's one possible polyatomic ion. And another one is sulfite, SO3 -2. Sulfite. So what we want you to do in the covalent box is basically try both the 8, so I'm going to say try 8 and the ite polyatomic ion and balance. So here's what I mean by that. Let's first do number 1, letter D. Let's do it with sulfite. So if I combine K plus 1 and SO3 minus 2, I'm going to get K2 SO3. Right? And if I do that, you're going to notice something pretty quickly. You have 2 Ks over here on the left-hand side. You have 2 Ks on the right-hand side. You have 1 S on the left, you have 1 S on the right. You have 4 O's on the left and 3 on the right. And that is never going to balance, right? Because you have O's coming from 2 different places on the left-hand side. There's 1 right here, there's 3 right here, there are 3 right there. If I have to change either one of those, I'm going to change the number of potassiums and the number of sulfurs, which means I'm going to have to put a coefficient right here. But that's going to change the number of oxygens, and it's this whole big mess that's never going to work, right? So that is not the right polyatomic ion to select. Instead, let's try sulfate. So sulfate is SO4 minus 2. If I make this K2SO4, now when I balance, if I have 2 Ks on the left and 2 Ks on the right, that's good. 1 S on the left, 1 S on the right, that's good. I have 1 plus 3 is 4 oxygens on the left and 4 oxygens on the right. So for these weird pink covalent compounds, what we want you to do is essentially manufacture a product that makes the balancing work correctly. And you're going to have a couple of choices for what product to make, and it's basically the 2 different polyatomic ions that you know. So we're going to try another one like that, and we're going to skip a letter here. We're going to go to letter F. So we're going to go to number 3, letter F, because you'll notice that here we are making an acid. A nonmetal oxide and water makes an acid, and we know something. We know automatically that the cation in an acid is H with a +1 charge, right? Hydrogen. And so now we have to figure out what polyatomic ion can we make out of the remaining stuff. So what do we have left? We have carbon, oxygen, and more oxygen. So we could make CO3 with a -2 charge, that is carbonate. Or we could make CO2 with a -2 charge, that is carbonite. Han Solo's nemesis, carbonite. All right, so we have some options. Let's try carbonate first. If I make carbonate my product, so carbonic acid, H2CO3, well, you'll notice that when we do that, the balancing works immediately, right? There are two H's on both sides. There is one carbon on both sides, and there are three oxygens. So that means that carbonate was the correct choice. If you tried carbonate, H2CO2, you'd notice that it will never balance for the same reasons we saw before. All right, so that takes care of all but letter E. And letter E, we are making a big kind of assumption here. So letter E, here's the problem. If this were a covalent, if this were an ionic compound, it would be easy, right? We could give this carbon a positive charge, we could give it like a +4 charge, we could give the oxygen a -2 and go forth. But we've already seen that carbon and oxygen can come together to make two different compounds. They can make carbon monoxide or they can make carbon dioxide. And so again, this is a very big shortcut that we're taking for Honors Chem, that you will learn different methods if you go on to a kind of a higher level chemistry class. But here's the assumption we're going to make. If you have a non-metal and oxygen, you are going to put them together as follows. You are simply going to add the subscripts and keep them the way they are on the left-hand side. So this one is going to look like math class. We're simply going to make this CO2 as a product, and when it balances, one carbon on either side, two oxygens on the other side, we're done. So we're simply going to just write out exactly what's given to us. So for instance, if we had something like, I don't know, let me just make something up. If we had, let's see, S plus O2, we would simply make this SO2, right? We're just going to recreate the product on the right-hand side with the same subscripts as we see on the left-hand side. So big time approximation. I know it's kind of weird and frustrating, but that one's actually pretty straightforward for you and simple for you if you encounter it on a test or a quiz.